Hi, welcome back to another video in our C++ machine learning tutorial. In the last video, we implemented the k-nearest neighbors algorithm, and in this video, we're going to implement another unsupervised learning algorithm, k-means clustering. I'll put a link in the description below to a resource describing what the k-means algorithm is. But just to summarize, k-means clustering seeks to cluster similar data points together as a method of classification. Each cluster consists of a centroid and a set of points that make up that particular cluster. The centroid is a vector where each element is the average of each cluster data point's feature vector at a particular index. So the value of the centroid at index I is equal to the average across all the points in the cluster at index I, if that makes sense. So training the k-means algorithm consists of assigning training data to a cluster that it's closest to. So we take a data point and calculate that data point's distance from the centroid of each cluster and find the closest cluster, and then add that query or add that training point to that particular cluster, and then update that cluster's centroid. Something to note about the k-means algorithm is that we have to hold all the training data in memory in order to validate the model. Training a k-means algorithm is trivial in nature, and the main portion of the work required is finding the best k for a particular data set. Additionally, we also notice that for k approximately equal to n, where n is the number of points in the training data, k-means simplifies to a version of k-nearest neighbors with the target number of neighbors equal to 1. Okay? So what we're going to do in this video, we're going to modify our data infrastructure. Because we're going to be using training data, validation data, and test data across all of our models, we can have each of our models inherit from a common data class, which will save us time in the future. We're going to create a cluster structure for the k-means algorithm. This struct is going to make it easy to work with clusters in the k-means algorithm. We'll also be able to use this in the future as well. Third, we're going to implement k-means. Fourth, we're going to validate k-means. In order to find the optimal k, we're going to employ an iterative approach within a range between where k is greater or equal to the number of classes in the data set. In this case, it's 10. And then have k also be less than or equal to the training data size times 0.1, or 10% of the training data size. And then we'll simply pick the best k that yields the highest performance, and then we'll test the performance of the optimal k with the test set. So with that said, let's get into it. So here I am in the k-nearest-neighbors.cc file, and what we're going to do is we're going to implement the common data class. So the common data class is just going to allow us to inherit from a common data class it's essentially going to allow us to make our code more reusable, so we don't have to have copies of the code throughout each model. So in KMeans.hpp, we see that we have training data, test data, and validation data, and as well as some setter methods here. So what we can do is, let's pull up our terminal. We're just going to clear this, and then we're in the top level directory, and then we're going to go to our include directory, and then we're going to touch common.hpp, and then in source directory we're going to touch common.cc. Okay, alright, so let's close. We can close KMeans.cc for right now, and I think that's all we need to do with the command line. So in common.hpp, we're going to keep with our method of operation here, where we say if in def, if not defined, common HPP, hash define common HPP, and then end if. Okay, so if you don't remember, these are preprocessor statements that are going to allow us to ensure that this header file is only included once across our whole project. Then we're going to do pound include data.hpp, as well as pound include vector. Okay, oops, not common.hpp, vector. And then now we're going to define our class called common data. And then put a semicolon here. And then all we're going to have is we're just going to say protected. And then we're just going to take this, these three fields from our K nearest neighbors, training data, test data, and validation data, cut that, and put it here. Okay? And then we're going to say public, and then we can copy these setter methods here, or cut those setter methods and put them under public. So now any model that that inherits from the common data class will now be able to have access to these members and these functions, these setter functions. Okay, so I think that's all we needed to do. Let's just clean up some of the spaces here, the vertical white space, just to make it nice. Okay, so now that we have common.hpp already made, we can just go to common.cc, and we're going to say pound include common.hpp, and then we can open up knearestneighbors.cc and take all of these functions and paste them in here, and then we just need to change this to common data as such. Okay, so that's all we really needed to do there. And now we can we're done with knn.cc, and we also have this these errors here because we haven't inherited from the common data class. So inside of knn.hpp, we need to say include common.hpp. And because we're inheriting from common.hpp, which also includes data.hpp, we can get rid of both of these include statements, and then we can say inherit from public common data. Okay, cool. So now that we have that all set up, this should update for us when we try to compile. Oh, yes, no, that's okay. Okay, so now let's go to this top level make file where we added some dependencies for object common.o, and then object common.o is dependent on source common.cc, and then we just add these other compile flags as well. So now that we're in the top level, we're in the source directory. All right, so now we can just call make, and it's compiling. Get a few warnings. Great. Okay, so our library compiled correctly, and now we can go to, so let's go to cd knn, and then we should just be able to just call make here as well. So let's clean everything, make clean, and then just call make, and there we go. So now let's just call main, and we see that nothing is really changed, but we're seeing that we're able to load the data structures accordingly, and we're also setting the training data, test data, and validation data, and we see that our algorithm is running like it was in the last video. Okay, great. So I'm just going to stop that, clear our terminal, and so we've added some reuse to our code, which is great. And something we're going to do a lot in this tutorial series is create new models. So to streamline that process, we want to create a new file called add new model. And this is going to be a bash script. So we can say, we put it in the top level directory. So we're going to say touch add new model.sh. And I can close all of these files. Okay. Close the terminal. And so in add new model, we're just going to say bin bash. And so what we want to check is we want to first check that the environment variable mnist mlroot is set. So we're just going to say if -z, which checks to see if the following string is empty. If this is true, then echo please define mnist mlroot, and then exit 1. Okay, and then fi. So now, if we get out of this, if we're past that if statement, then we know that we know that we're in the correct location. Okay, so what we want to do is let's see. So we want to create our dir is equal to echo whatever we get as an input, and then pipe that to change the case from lowercase to all uppercase. Okay, so that's what this code does, and stores it in dir. So our model name lower. I'm sorry. This takes, so this line, let's add a comment just so that we're not, makes input all uppercase. And then this next line will take the input and make it all lowercase. Echo, TRAZ, AZ. Okay? So what that'll allow us to do is make the top level model directory all uppercase. That follows our convention here. So K nearest neighbors is all uppercase. And then the model lowercase is the convention that we create a KNN.CC and an HPP, or KNN.HPP, which is lowercase. So what we're going to do now is make dir and also make the parents, so mnist mlroot /dir /include, and then mnist mlroot dir /source. So this creates an include directory and a source directory. And then we want to create some files. We're going to say touch mnist mlroot /dir /makefile, because every model is going to need a makefile. And then we're going to say touch mnist mlroot dir include model name lower .hpp. And I think we need to surround this with quotes. Okay, and then we can copy this line, and then this is going to be in the source, and this is going to be CC. Okay, Cool. So that's all we needed to do to basically be able to type in add new model.sh and then space whatever the name of the model is. Okay. So oh, and by the way, the $@ symbol is just what is just the entire command line after the model was after the script was called. So let's change the permissions to be plus executable to add new model.sh, and then we're going to say add new model KMeans. Okay, so as you can see up here, we have a new directory with KMeans, then we have an include with KMeans.hpp, and then a source file as well. Okay, great. So that's going to help us later as well. It's just going to make it really easy to say, if we did this again with add new model neural network, we see that neural network was created with an include and a source file. Great, cool. So we're going to say remove our neural network because we don't need that right now. Okay, so let's now jump into creating our KMeans algorithm, or implementing our KMeans algorithm. Okay, so let's go into KMeans.hpp, and so as usual, if and def KMeans HPP hash define KMeans HPP, and then end if. Okay, so we're going to need to include common.hpp. Common.hpp. We're going to need to include unordered set. Include include limits. We don't need to include vector because vector is included in common.hpp. Pound include C standard library. Include C math for square roots when we calculate distances. And then pound include map as well. All right. And then last but not least, data handler HPP. Cool. Now we're going to define our struct cluster. So we're going to say type def struct cluster. And so this type def, we're going to cluster T, is just going to contain two fields, four fields. A centroid that's of type vector, that is of type double. We're going to have cluster points, which is going to be a vector of type data. And then we're going to have a map that counts our classes that are currently in the cluster. And then an integer value that captures the most frequent class of the cluster that occurs in the cluster. Okay, and then we're going to have some methods like a constructor, and then an add to cluster method, and then set most frequent class, which is going to allow us to keep track of the most frequent class so that we don't have to calculate it every time we want to query the model. Okay, so let's start off with implementing our constructor. So cluster, that's going to take in a pointer to some data called initial point. So each cluster is going to be initialized with a initial data point, and then we're going to say centroid is equal to new standard vector of type data, or of type double, excuse me. And then the cluster points is equal to new standard vector data pointers. Okay, so didn't define my field, so standard vector double is going to be a pointer, and we're going to call it centroid. And then standard vector data pointer and cluster points. Okay, and then we have a standard map of an int, and it's going to be class counts. Don't really need to allocate that on the heap because the size of the class counts map is going to be hopefully not that big. On the order of number of classes in the whole data set. And then we're going to have int most frequent classes, or class. Okay? Alright, so now we're going to say for auto value in dereference of the initial point that get feature vector. So we're iterating over each value in the feature vector. And then we're going to say centroid pushback value. Okay? So we're initializing each centroid with the value of the first data point. Okay? And then we're going to say cluster points pushback initial point, and then class counts of initial point that get label equals 1. Okay, so we're initializing the class count of the first class that we see to 1. And then we're going to say the most frequent class is equal to initial point get label. Okay. All right. So cool. So that's our constructor for our cluster class. And then we're going to say void add to cluster. And then this is going to take a data point. So what we're going to need to do is update the running average of each cluster, or each centroid value. So in order to do that, we need to keep track of the previous size of the cluster, add the new point to that cluster, and then update, then do a running calculation of the running average. So to calculate the running average, we multiply by the previous size, multiply the value at index I by the previous size, add the new point at that index to val, and then divide the value by the number of points in the cluster, and then we add that value, re-add that value to the centroid. Okay, so it's a pretty standard running average algorithm. So int previous previous size is equal to cluster points size. Okay, and then cluster points pushback point, and then for int I is equal to 0, I is less than centroid.size I plus plus. I don't know if we want to do that because we pointed, so we want to say size minus 1. So we want to go up all the way up to the end minus 1 because we added the new point to that value. Okay? Okay, so now double value is equal to centroid at I, and then val times equals previous size, and then value plus equals, sorry, this needs to be value plus equals point that get feature vector at I, and then val divided by equals double of cluster points size. So the new size of the cluster. Okay? And then centroid dot at I is equal to val. So we just update that value at that particular index. So now we need to say, we need to add the class to the class count. We need to update the class counts matrix. So if class counts find of point get label is equal to class counts end. So if we didn't find it, then we want to say class counts of point get label is equal to 1, else class counts of point get label plus plus. Okay, so that's all we need to do when we add a new value to a cluster. And then we need to write a function that sets the most frequent class. So void set most frequent class, and int best class. This is pretty standard. And then int frequency is equal to 0. And then for auto key value in class counts. Sorry, let me give us some space. If kv.second is greater than frequency, then frequency is equal to kv.second, and then best class is equal to kv.first. Alright, so that's just allowing us to set the best class, and then most frequent class is equal to best class. Okay, so now that we've implemented our cluster, let's add in our class KMeans, which is going to inherit from common data. Okay, and then we're going to say int num clusters. So our field, we're going to have some fields called number of clusters. We're going to have a vector of cluster types. That's just going to tell us the number of clusters in our model. And we're going to have an unordered set that's going to allow us to keep track of which values in our training data that we've used, which is going to help us not have to mutate the training data, so not have to delete or add new members or reset the training data. We'll just be able to reset that unordered set and clear the clusters as well. Okay, so we have those three fields, and then we're going to have some methods. We're going to have our constructor that's going to take in a value k. Then we're going to have a void method called init clusters, which is going to allow us to initialize our clusters. So pick a random point in our training data and add that, and create a new cluster at that with that data point. And then we're going to have an initialize clusters for each class. So because we expect the like data points to cluster together, it might stand to reason to have the number of clusters equal to the number of classes in your data set, and then allow your data set, and then force each cluster to initialize to a particular class. So you have one cluster of zeros, you have one cluster that starts with a cluster of ones, etc., etc. And we'll implement both of those to see how the performance works on both of those. Then we're going to train our data model, which is simply just iterating through all of our training points and adding them to the closest cluster that they belong to. We're going to implement a utility function for Euclidean distance. And then we're going to implement a validate function, which we're going to test our K clusters against our validation set. And then we're going to implement our test function that's going to, given the best K, we're going to run the test set against that, that model. Okay? So let's implement these. So int num clusters, and then we're going to have a standard vector of cluster types, and then they're going to be pointers, and then we're going to have we're going to just call it clusters, and then we're going to have a standard unordered set of type integer, and then we're going to have used indexes. Okay, and then so public. So these are all those are all members. So KMeans, so our constructor, we're going to take an int K, we're going to have a void init clusters, void init clusters for each class, and then void train, double Euclidean distance. I'm just going to take in a centroid, so a standard vector of doubles. It's going to be a pointer type, and then we're going to have a data point as well. Okay, and then double validate, and then double test. Okay, so now let's take this information, and we're going to let's take this class definition, and we're going to implement it in our KMeans.cc file. Okay, so let's open up KMeans.cc, and then we're just going to include KMeans.HPP, which is nice because that's the only include statement we're going to need, because we're including all of this stuff in our header file. Class counts, standard map, expression, oh, it's not a pointer. Okay, so let's just fix that. And then this needs to be value. And then I need a semicolon here. And this needs to be value as well. Nice. Okay. So in public, we're just going to copy these. Actually, let's copy this. And we're going to paste. Great. And then we can fix the formatting a little bit. Okay. And then KMeans. Okay. Oops. Okay. And okay, so I just added the class prefix to those methods, so it knows what object these methods belong to. All right. Let's see, why is it yelling at me? I think we're okay. All right, so given K, so our num clusters is going to be equal to K. Clusters is equal to new standard vector of cluster type, pointer, and then used indexes is going to be equal to new standard vector, or no, standard unordered set of type int. Nice. Okay, so now our init clusters method is just going to say for int I is equal to 0, I is less than num clusters I plus plus. We're going to say int index is going to be equal to rand modulus training data size. So what this is allowing us to do is basically get a value of between 0 and the training data size minus 1. So if our training data has 12,000 points, we're going to have a point between 0 and 11,999. Okay. And then so say while used indexes find of index is not equal to used indexes end. So what this is saying is while we haven't, while we have found the index in used indexes, we want to then recalculate a new index. It's not super efficient, but it's a workable solution. So then we're going to say clusters pushback. No, I'm sorry. Clusters. Yes, clusters dot pushback new cluster of training data at I, or at index, sorry. Okay, and then used indexes insert index. So that way we don't re-add the same cluster to a particular, initialize a cluster to the same index. Okay, so that's one. So this init clusters for each class method is similar, but what we're going to do is we're going to say standard unordered set int right, class is used. So for int I is, we can just copy this, put this here, and then what we're going to need to change is say if right, okay, so instead of iterating over the number of clusters, we're going to say for int I is equal to training data size, and then we're going to just say if classes used dot find training data at I get label is equal to classes used dot end. So if we have not used this class before, we want to initialize a new cluster and add it to the list of clusters. So we're going to say new cluster T of training data at I. Okay, and then classes used dot insert training data at I get label. Okay, and then used indexes insert I. So we still need to keep track of what index we've used in a particular class, regardless of it whether we used it in. So basically, we don't want to reuse this when we train our model later because it's using duplicate data. Okay. All right. Let's see. Dot end. I'm used to using pointers. Okay. So now we can implement our training algorithm. So this is very similar to init clusters, but we're just going to do it while the used index's size is not equal to the training data size. So we're just going to say while used indexes dot size is not equal to, or I guess less than training data dot size. Int index is equal to rand mod training data size, and then we can take this top and we put it right here, and then we say so now we need to figure out which cluster to add this point to, now that we have found an index that we haven't used already. Okay, so we're going to say double min distance is equal to standard numeric limits double max, so the max value of a double, and then we say int best cluster is equal to 0. So basically we're saying no matter what, the best cluster is going to be cluster 0, which is not going to be the case. So for it, not necessarily going to be the case. So for int j is equal to 0, j is less than the clusters dot size, j plus plus, and then double current dist is equal to Euclidean distance of training data, or I'm sorry, clusters that at or I centroid, and then we want to pass in the data point. So training data at index. Okay, so then if, you know, this is the usual. So if current dist is less than min dist, then we just say min dist is equal to current dist, and then best cluster is equal to j. All right. So then outside of this for loop, we say clusters at best cluster, add to cluster, training data at index, clusters at j, excuse me, and then we say clusters. Oh, so one thing that we need to fix is that in our cluster structure, we need to, every time we update add to cluster, we need to just say set most frequent class. Okay. Nice. Okay, and then we say used indexes insert index. Great. And then Euclidean distance, so this is going to be double centroid, and then this is data point. So Euclidean distance, I mean, we've implemented this before. This is going to be something that we might want to abstract out later, but for now we'll just implement it again just to refresh our memory. Int I is equal to 0. I is less than centroid dot size, centroid size I plus plus, and then dist plus equals pow centroid at I minus point get feature vector dot at I, and then square that. Okay, so remember that Euclidean distance is the sum of the differences between each point at the ith index squared. And then we square root that. So we're just going to return square root of dist. Okay. And then our validate method is very straightforward. It's similar to as if we're finding the closest cluster and then just going to compare that the label or the most frequent class of that cluster is also equal to the current query point class. Okay, so we can say we can take this. We're not going to add it to the cluster, so we can just take this. But first we need to say double num correct, which we're going to use later to calculate the percentage performance. Double num correct, and so for auto point query point in dereference validation data. So for each point in there, we're just going to say command V, double min dist is equal to this, and then we get the we're just going to say query point at J. No, I'm sorry. We're just passing in query point. Right. Okay. So that gives us our Euclidean distance, and then so now we say if clusters at best cluster most frequent class is equal to query point get label, then we just say num correct plus plus. So that means we would have added it to the correct cluster. Okay, so in some implementations they say that you should actually add the query point to the new known search space. So we would add this query point to the best cluster and then recalculate the centroid accordingly. So that way the model, that particular cluster, then is more likely to be correct for that particular class, more likely to cluster around other similar points. Okay. In this implementation, we're not going to do that right now. So we're just going to say return 100.0 times. So we're just going to take multiplied by the percentage. So num correct divided by double validation data size. Okay, nice. Okay, and then to test is identical. It's just instead of validation set, we're just going to use the test set. So test data, and I think that's it. Test data dot size, num correct. Okay, great. So this all looks fantastic. So let's implement our main method here. So we're going to say int main. I like doing it this way. Int main. We can take all this this data handler stuff from the K nearest neighbors implementation. So we can say we can take all of this here and then implement it here. We may actually be able to abstract this out, so I'm going to try that and then in one of the future videos. But so that way we don't have to call it every time, or have our main method have this extra stuff in it every time. It might just be able to. We'll probably just be able to call it as a part of the common data class. Okay, so now we just want to say calculate the double performance is equal to 0.0, double best performance is equal to 0.0, and then int best k. And we're going to initialize k to be the training, or I'm sorry, the number of classes, but actually we don't need to do that. So we're just going to say for int I is equal to 0, I is less than dh.get class counts, which we don't have implemented yet. Or I'm sorry, this is not what I wanted to do. So I'm going to say int k is equal to dh.get class counts. K is less than dh.get training data size times 0.1, so 10% of the training data, and then k plus plus. We're going to have to implement this get class counts method. So then we're just going to say initialize a new KMeans. So a new KMeans with k as our value, and then we're just going to say km.set training data is equal to dh get training data, and then we can just copy all of this and just say set test data and get test data, and then set validation data, and then get validation data. Okay. All right, and then we're going to say km init clusters, and then km train, and then performance is going to be equal to km.validate, and then printf current performance at k is equal to %d is going to be %.2f. We just want to go up to 2 decimal places, and then we're going to pass in k and then performance. Okay, we need to throw a backslash in, or else we won't be able to read it. And then if performance is greater than best performance, then best performance is equal to performance, best k is equal to k. So like best int best k is equal to 1, just, you know. And then outside of this loop, we want to do this all over again, but we want to see what the performance was with our best k on the test set. Best k, and then instead of train, we want test. KMeans. Yeah. All right, so this won't compile. So this is inaccessible. Why is that inaccessible? Because, did I set it as protected? Yeah, I did. Okay. Did I set the functions as public? Yeah, I did. Okay. All right. So this is going to be best k. Tested performance. I don't need any of this. Init clusters km test. Alright, so now let's go into our data handler, and then we're just going to, down here, we're going to say standard vector, no, we just want to return a class counts number, I believe. Let's see. Get class counts, yeah, okay. So, yeah, we're just going to return an int get class counts. Yeah. So now, just take this and in data handler.cc, get training data, and then this is just going to be data handler, and then return num classes. Okay. Cool. Let's get rid of this. KMeans CC. Okay, so let's, last thing we need to do is we need to create our make file. So our make file, we can just copy from K-nearest neighbors because it's almost identical. So KMeans, we don't need this preprocessor flag. KMeans, KMeans, and I believe that is it. Okay. Now we need to say, so in mnis ml root, we're just going to call make. Actually, before I do that, let's just call make clean. And let's call make. Awesome. So cd KMeans, and we're just going to call make. Okay. So I didn't declare this, excuse me, public. Whoops. And that should fix all of these errors that I was seeing over here. I think. Yeah. Let's try that. Oh, get training data is a method. So it's yelling at me at 125, yeah. Am I doing that anywhere else? Let's try it. Oop. And it's also saying that get label is not a member. Line 50. Get label. Where am I calling this? So let's see. Command F. Oh, not in there. Command F get label. I'm calling it there, and there. KMeans.hpp. So let's try this again. Awesome. So we compiled, and let's run it. So we're getting the file header. This is all new. Not new. All right. Got all the classes. Okay, So let's see how it does on this first go around. So in this first iteration, we're creating 10 clusters for the 10 unique classes. And let's see. Okay, so here's our first run. So our K is equal to 10. Performance is 57%. Honestly, I was expecting a little bit better, but let's let it run for a few more iterations and see what we get. See, let me just make sure that in our cluster class we are, okay, so that sets that, and we're updating the most frequent class accordingly. Okay. Cool. So another reason why this is pretty slow is that we are retraining the model every time we test a new K value. All right, so we have a little increase in performance there. You know, resetting the training and validation data, reinitializing the clusters, which really shouldn't take too much time. But the training is what takes the most time because we're trying to assign 12,000 minus K training points to the correct cluster, which doesn't seem like it should take too much time. I mean, I think this part here is, well, when you initialize, it doesn't really matter. But when you train, I think, yeah. So I think we can speed this up a little bit. So instead of, you know, randomly picking values. So like you can imagine if you get to like 11,000 out of 12,000 used points, then it's going to get harder. The more points you use, it's going to get harder and harder to find a random value that's going to be that one that you haven't used. So what we can do instead is we can say int index is equal to 0, and then you say while that's not the case, we just say index plus plus. So let's just remake, and let's go main. Right, so instead of instead of just trying to find pick a random value in the training data and add it to a particular cluster, we just sequentially go through and find an index that we want. And then in validate, we're just going through sequentially as well. So still a little slow. Oh, training data is 45,000 points. Sorry, excuse me. We see our performance slowly increasing. I'm going to let this run for a little while, and I will get back to you with the results. Here we are back at the KMeans results, and here we see with a cluster count of approximately 484, we get about 92% accuracy when predicting against the validation set. Today is Tuesday, and I recorded this video on Sunday, so I let this run for about 2 days essentially, and we're only at we're only 10% of the way through our validation portion, because the training data set is 45,000 points. We said 10% of the training set, the K size is going to be up to 10% of the K size, or 10% of the training data size, and that would put K at 4,500. So it would probably take another, say, 30 days to run up to 4,500 K. But this is pretty good performance, given that this is an unsupervised method of training our algorithm. Based on the previous video with K-means, we saw that K-means was much better at smaller values of K, and that makes sense given that, you know, like points are going to be closest to each other, rather than a cluster. The average value, the average centroid of a cluster might not necessarily be closer to its correct class, if that makes sense. So given that, I hope you enjoyed the video. Next time we will start with our neural networks, and we'll start by implementing a radial basis function neural network, which will expand. We'll seek to continue upon the premise of using centroids as a part of our learning algorithm. So I think we're done with unsupervised learning for now, and then all of the techniques that we're going to see from here on potentially are going to be supervised techniques. We may implement an autoencoder, which is an unsupervised version of a neural network, but other than that, we're probably going to do some mostly supervised learning models. So with that, thanks for watching, and until next time.